Okay, so this is where we were. Well, actually, we were further down here. I kind of skipped over that first part last time. Come on, where's my mouse? Oh, come on, don't do this to me. Ah, there it is. It's not working. Okay, there it goes. All right, so I'm recording. Of course, when I started to screw up, I started recording. That's always the way it works. All right, so last time we were working on buffers, and I skipped this first part, but I'll probably go back to that. But I just want to go over what I was doing last time. Okay, so we have a situation here. So by the way, this week is kind of dedicated, at least mostly, to buffers, because we're doing it in lab as well. And so I did an example on Monday of a buffer solution. So as you can remember, I hope you remember, a buffer solution contains a weak acid and its conjugate base. And the acid and base combination that I used in this example are carbonic acid, which is H2CO3, and bicarbonate, which is HCO3 minus. So this is the acid and conjugate base. These are the pairs for this buffer. And there are significant amounts of both of these in here because we're dealing with a 0.371 molar solution of carbonic acid and a 0.35 molar solution of sodium bicarbonate. So that supplies 0.350 molar of bicarbonate. Now, last time, what I did was I showed you how we can use this equation. This is called the Henderson-Hasselbach equation. Actually, the equation is in general is just this. pH is equal to the pKa of the acid. That would be the pKa of H2CO3, which is the negative log of the Ka of H2CO3, which is calculated right here. Okay, so this is the Ka, and we take the negative log of it. And then we take the ratio of the concentration of the anion. The anion is another word that we use for the conjugate base. And sometimes it's referred to as A minus, the concentration of the anion. And the acid is, in general, we call it HA. And so that's why there's this notation here. So in our case, we had 0.350 molar of the H2CO, sorry, that's the HCO3 minus, that's the bicarbonate. And this was the H2CO3. I was pointing out here that when you have a smaller number on top of this ratio, you end up with a number that's less than 1. You're taking the log of, you have to take the log of this whole thing, right? And that would become negative because the log of a number that's less than 1 is negative. Log of a number greater than 1 is positive. And so here's just a pretty simple recipe, if you will, to figure out the pH of a buffer solution. So you simply add the pKa, which is given here, with this log of this ratio, and you get a pH of 6.34. Now, there would have been nothing wrong with doing the problem in the old-fashioned way, which is using an ice setup, okay? So I went over that last time, but I could just as easily, well, I think it's a little harder. That's why I recommend the other way in the first place. But you could have done it this way. you will get exactly the same answer. So you would write the acid dissociation equilibrium. Okay, you would start out by putting your initial concentrations. Okay, and of course you don't worry about the water. This would be 0. And then you would fill in the ice chart, minus x, plus x, x, 0.371 minus x, 0.350 plus x. Okay, and I did a buffer problem like this once, but I'll do this one again. And you know, you look at it at the start, and it looks really perfectly awful, right? And this is equal to Ka, which is 4.3 times 10 to the negative 7th. That's the Ka for H2CO3 from the chart. Looks terrible, but it isn't terrible, because this is a problem where you have the acid and its conjugate base. If you only had the acid, you'd have to justify neglecting the X by looking at the magnitude of the Ka, 100 times the Ka, and the initial concentration of acid. This initial concentration is certainly more than 100 times the Ka. But in a problem where we have also added HCO3 minus, that drives the equilibrium backwards. And so you have an even smaller X. So you can always neglect X in buffer problems. You don't even have to justify it. And the reason for that is that the added conjugate base makes this equilibrium even further to the left. So X is even smaller in a buffer problem. So that means I can cross out both of those X's. And so I just have this much more simple equation to solve. Just check something. Okay. And that's 4.3 times 10 to the negative 7th. So I would just cross multiply. And so I would just divide both sides by 0.350. And I would get that X equals these things. It comes out to 4.6 times 10 to the negative 7th. And so that the pH, it's actually 4.56 if I keep an extra digit. The pH becomes 6.34, which is no surprise because that's exactly what we got here. So this is the same. So if you really want to do a problem in the old-fashioned ice way instead of the new lovely Henderson-Hasselbach equation way, we call this the HH equation. Okay, you get the same answer. So of course, it makes sense. So the next thing I did last class was to figure out what happens if we add strong acid to the buffer. Okay, and that's about as far as I got. I mean, I went over it and I went over what happens. And what happens is, and first I've written it in the general case, that when you add strong acids, such as, for example, HCl or HBr, any of those 6 strong acids, that's like adding H3O plus, okay? So that's just like adding H3O plus, because as soon as it hits that solution and it gets spread around, the HCl would dissociate or donate a proton to water, however you want to look at it, and give you H3O plus. So this is from the strong acid, okay? And that would immediately react with the base. This is the conjugate base. This is the anion, that's what we call it. That's present in a buffer solution, and you would generate the weak acid here and water, okay? So what that does in every case is it decreases that concentration of the conjugate base, or A minus, and it increases the concentration of the weak acid, the HA. And so in the specific case of the H2CO3, HCO3 minus buffer solution, you see that the bicarbonate reacts with H3O plus. You know, it makes sense. H3O plus is acid, bicarbonate is basic. So a proton will be donated to get the weak acid and ends up with water. So in doing this, the concentration of the H2CO3 increases. You add H3O plus, you get more H2CO3 in the solution and less HCO3 minus. That will push the pH down a little bit, but it won't push it down a lot because we no longer have H3O plus, a lot of it floating around in there. The HCO3 minus, in a sense, has sucked out the H3O plus. So the base in the buffer has taken out that strong acid and converted it basically to weak acid right here. So we have an increase in the concentration of weak acid and a decrease in the concentration of the base. And so I show the consequence of this here. So when you do this, the first thing you have to calculate, this is something we also do in lab this week, is, you have to say, okay, we're adding, in this problem, we're adding 1 milliliter of 6 molar HCl to 200 milliliters of the buffer. So there I have my 200 mils of buffer. I'm adding 1 milliliter of that HCl solution. So I am effectively making a dilution. I'm taking my 1 milliliter of 6 molar HCl and diluting it to a total volume. Okay, so now I have to add together what volume I had originally and the 1 milliliter. So 200 plus 1 is 201. So total volume of 201 milliliters. So when I do this, MdVd is MCVC. Here is this is the original concentrated solution of the strong acid, the 1 milliliter of 6 molar. This is Vc, which is 1 milliliter, and this is Vd, the total volume of the diluted solution. And when you do this, you get approximately 0.03, but I really should keep 2 sig figs. So I could call it 0.030 molar because I had 2 sig figs here. So I just always like to keep an extra figure and round at the end. So what I had for the HCO3 minus, the initial concentration was 0.350 molar. That goes down by an amount equal to the amount of H3O plus that was added. And so when you subtract, you get 0.320. For the acid, I have to add 0.0299 because however much H3O plus was added, that's how much that reaction here that I showed you before, that's how much this reaction here is going to go forward and increase the amount of the HA. And so now I just have different numbers here. I have 0.320 on top, 0.401 on the bottom. And so now I get a pH of 6.27. The pKa here is the same because it's the same acid dissociation equilibrium. So what happened was the pH went from 6.34 to 6.27, not a very big change. And that's why we call it a buffer, because it buffers, it mitigates, it lessens the change in pH. But, you might very well ask the question, how does this compare to adding the same amount of HCl to water instead of the buffer? So let's figure that out because we know how to figure that out. So basically we're asking, if you dilute 1 milliliter of 6 molar HCl and you add it to 200 milliliters of water, so you end up with 201 milliliters. You're asking the question, what's the concentration of H3O plus in that solution? Well, we already calculated that. We already did it. It's the same exact dilution calculation as we did here. Okay, so this is redone. Just redo it right here. Or you could just write the same answer, but just to be complete, this is the same dilution calculation as before. Of course, before we used that much HCl and we said, okay, now we have a reaction with the base in the buffer, but here we don't have a buffer. So we just have that much H3O plus. So it's the same thing. It's 6 molar, 1.0 milliliter, I think 6.00 divided by 201 milliliters. I just want to mention for those of you who are really, really closely following this, that when I do this dilution and change the volume, don't worry about this unless you thought of this. We had this concentration here for the buffers. I don't readjust those concentrations even though I changed the total volume. So I really should adjust those concentrations. But whenever I give one of these problems, I always give a very small volume of a strong acid so that it really doesn't change the overall volume very much, so that I can leave these concentrations of HCO3 minus, these initial concentrations, the same. I don't have to adjust them. If you look on the internet, I'm sure you'll find much more complicated equations about how you now have to readjust those initial values, but I'm not going to do that in this class. So this again comes out to 0.0299 molar, really 0.030 molar. And so now all I have to do is that tells me that the H3O plus concentration is 0.0299 molar. And I just have to take the negative log of that. And when I do that, let's see what I get here. I get 1.52. All right. So what does that mean now? So that means that if I had distilled water with a pH of 7, and I added the 1 milliliter of 6 molar HCl to 200 milliliters of the buffer, the pH will go from 7, because distilled water has a pH of 7, to 1.52. So this is what happened to distilled water when you added that acid. What happened to the buffer? Just to give you a contrast here, it went from 6.34 to 6.27. So this buffer is really doing its job. Note this here, every pH unit is a factor of 10 in acidity, acidity being the concentration of H3O plus. So there are literally, from 7 to 2, is more than 5 powers of 10 change in the H3O plus concentration. Here, there isn't even a 0.1 pH unit change. This is a very slight change in pH. So the buffer is really doing its job. Does anyone have a question about that? Any question at all? I'm happy to answer any questions.
I actually kind of have a hypothetical question, I guess.
Sure.
So if you put enough acid in or base into a buffer, could you run out of?
Yes, absolutely.
In
fact, I don't know if you had a look at the questions for the lab that I did yesterday. So what he's asking is, can this go on forever? And the answer is no, of course not. Depends on how much you have. can you continue to add acid forever? And the answer is no. What happens is you have a certain concentration, in this case, of these two things. Okay, suppose I have, so this was 0.350, 0.371. So what if I add acid so that my H3O plus concentration is 0.4? Well, yeah, sure, 0.350 of it will be changed over to the weak acid, but this number is greater than this number. So I don't really talk about buffer capacity in this class, but that's basically what it means. The buffer capacity is, how much of that added acid, how much acid can be added before you overcome the amount of base that's in your solution. So here you could add up to 0.350 and you would have enough bicarbonate to react with it. But if you added 0.4, that's too much. 0.4 is greater than 0.350. So we would say it exceeds the buffer capacity. So that was a very good question. Thank you. Okay, so the next thing I'd like to do is talk about what happens when you add base to the buffer. All right. This computer is getting hot. I gotta get the fans closer. Okay. All right, so let me go on to adding. So now we're going to do is add the same amount, 1 milliliter, but this time it's 6 molar of strong base to 200 milliliters again of the original buffer. Okay, so what do you have to do first in this problem? Well, what we have to do is figure out what happens to the OH minus ions. Okay, so first of all, we have to calculate what is the concentration of the hydrogen, just like we calculated the concentration of the H3O plus. What is the concentration of hydroxide immediately after adding the NaOH? And again, this is a dilution problem. And in fact, it's the same dilution problem, because we're taking, 1 milliliter, that's VC, of 6 molar, that's MC. This time it's NaOH, so that's the, or OH minus, okay. And we're going to have a total volume at the end of 201 milliliters, so 200 plus 1. So that's going to be VD. So MD is MCVC over VD. So that's like, this is the same calculation. 6 molar, 1.0 milliliters over 201 equals 0.0299 molar of NaOH, which is also 0.0299, oops, too many O's, molar of OH minus. So that is the concentration of hydroxide that we have put in this solution. So that's number one, what is the concentration? And number two, what does the OH minus do? Okay, OH minus, that's a base. What is a base going to react with in the buffer? So we have two choices. We have H2CO3, that's the acid, and we have HCO3 minus, it's the conjugate base or the anion. So what will hydroxide react with? Which of these components?
H2CO3.
That's right. And it will accept a proton because it's a base, giving water and HCO3 minus. So the difference between adding an acid and adding a base is that the base reacts with the acid in the buffer. So this decreases the concentration of H2CO3, whereas when we added H3O plus, it decreased the amount of HCO3 minus and increased the H2. So it's just the opposite. It decreases H2CO3, it increases the concentration of HCO3 minus. How much? Well, by the amount of OH minus that was added. So we had for the H2CO3, we had 0.371 molar. Okay, now, boy, I see I don't have anywhere near enough space here. That's okay. Okay. No, it didn't work. So now we have 0.371 minus 0.0299 equals 0.341. And for the HCO3 minus, we had 0.350. Now we're going to add the 0.0299, and we get 0.380 molar. So now in the Henderson-Hasselbach equation, or in this case, so the pKa is still the same. It's still the negative log of 4.3 times 10 to the negative 7th. That's the pKa of H2CO3. And that is 6.367, keeping an extra digit. Plus, okay, so now I have the log of 0.380 divided by 0.341. You can see now the numerator is greater than the denominator, so this is going to be positive. And so this comes out to 6.41. So you can see that the pH went from 6.34 to 6.41. Not a big change. So the buffer is doing its job. Okay, but of course you might ask the question, what would happen if you added that buffer, if you added it to water, if you added the NaOH to water instead? Okay, well, the pH of water, again, is 7. And now, what is the pH if you just add the NaOH, 1 milliliter of 6 molar to 200 milliliters of water? Well, we've done this calculation 3 times now, right? It's the same dilution calculation. So the molarity, MD, which is the molarity of the OH minus, is 0.0299 or 0.030 molar. And so the POH is the negative log of that, which is 1.52. And so the pH is 14 minus 1.52. Notice that was what the pH was in the previous example because we added the same amount of acid. So this comes out to 12.48. Okay, so that you can see that's extremely high pH. So the pH of distilled water went from 7 to 12.48. The pH of the buffer went from 6.34 to 6.41. It's really a huge difference. Okay, does anyone have a question about that? I do want to point out that if you wanted to, you could use the ice type of problem to solve this as well. And you could do this for adding acid as well. You would have to start with the same equilibrium. Oops. Right? So we had 0.371 in the original buffer. So that's the original buffer. These are the initial concentrations. So then what happens is then we have a new initial set of concentrations. So after the hydroxide is added, the 0.371, right, that changed. It became 0.341. And the new base concentration became 0.380. And so you could set up an ice chart with that new set of concentrations. Put a 0 for H3O plus, you put minus X, 0.341 minus X, 0.380 plus X. This would be X. So it's exactly the same type of calculation that we've been doing all along. It's just that now we have these new initial concentrations, whereas before we had these two. So you could solve this problem the same way that we know how to do it from before. Again, this is a buffer problem. We could ignore X without even having to justify it, and it's still equal to the same Ka, which is 4.3 times 10 to the negative 7th. Okay, so you could solve it this way if you wanted to. You would get the same answer for the value of the pH. Yeah, I don't know if I have that here. Yeah, no, I'm done with that. You could, it would get the same answer. But I just wanted to tell you that because I know some people every year always seem to want to do it the old-fashioned way. Old habits, you know, you learn how to do something, you want to keep doing it. So between what I did in class today and what's going on in lab this week, I think that gives you a fair amount of experience with buffer solutions. Anyway, so I'm going to move on to the next subtopic, which is acid strength, that I'd like to talk a little bit about, unless somebody has a question. All right, well, if you think of one, you could save it for the end. All right, so I'd like to talk a little bit about a totally different topic. Well, it's not totally different because it's still about acids, but I actually haven't said much about this in covering this. So I have talked about how Kas for acids are very variable. You know, they really do vary all over the place. As they can be as low as 10 to the minus 10th or really even lower, and as high as like 10 to the 10th for strong acids. Somewhere in that, you know, so it's a huge, it's a 20 order of magnitude ballpark. So that means that some acids really, really readily donate their proton. They immediately dissociate completely. And other acids only do it very occasionally. So the question becomes, you know, why do some acids, you know, readily give up their proton and others do so only occasionally. Okay, so and so really what we're asking here is, what determines the strength of an acid? And really, you should think about the strength of an acid as its willingness to donate a proton. You could say to water, because that's usually how we write the acid dissociation reaction. But when you take organic chemistry, you don't deal with a lot of aqueous solutions. So you might have the same statement, but maybe it wouldn't say in water. Okay. Okay. So what I want to do is start by looking at the basic structure, basic, no pun intended. So I'll just write structure of any acid. And there are features I'm going to add later. Let's say you have an atom that's not hydrogen. So X is atom that is not hydrogen, bonded to a hydrogen. This is going to be a polar bond, really has to be a polar bond for this to be an acid. That's not the only requirement though, as I'll show you. And then we have the part of the molecule that I like to call the etc. Okay, that's really like the rest. And I'll talk some more specifically about that. So we have the atom that directly holds the donatable hydrogen. That's this X here. And then we have the rest of the molecule. So what the acid strength depends on very basically, first of all, is the polarity of the XH bond. Okay, so it really has to do with how delta positive, how positive is the hydrogen. So this has to do with the electronegativity of the atom X. And what is X most of the time that we've seen in this class? Many X's are, many times X is oxygen, but it could be chlorine or fluorine or bromine, and there's different things it can be. Okay, so it has to do with the electronegativity, which is why I put an electronegativity chart under Unit 6, so you have it to refer to. So the thing is that the more delta positive the hydrogen is, the more it's already like a proton. And the more easily it is donated. So that's the first thing. It has to do with the polarity of the that bond. But the second thing, which is very closely related, has to do with the strength of the XH bond. So what do you think about that? If this bond is stronger, what do you think? Do you think that that H will be held more or held less? If it's a strong bond, right, that means that those two are more attracted to each other. So if XH bond is stronger, then the H is held more strongly. It needs more energy to break apart, okay? So if that bond is stronger, so, and the acid will be weaker. Okay, so we have the fact that we have the bond polarity, and then we have the strength of the bond. Now, what does bond strength depend on? This is not something that we study really a lot, but mainly it depends on how close those atoms are to each other. So bond strength depends largely on the bond's length. The longer the bond, the weaker the bond. Okay. So very small atoms will have strong bonds, short bonds, strong bonds. Okay, so that's two factors, but there is a third factor, and the third factor is this etc. And so I just want to say that the rest of the molecule matters also. Wow, it's been a long time since this thing froze on me. It's funny, I have a dummy monitor, and the dummy monitor is still working fine, but the surface is not at all working fine because I hit the X and the dummy monitor immediately got rid of the program, but I'm not going to be able to get the little computer to do that, even with the fans, but well, whatever. Let me try to get rid of this. Now it's being really... Wow, it's really going to be bad this time. Bear with me here. I'm sorry. I'm not happy about this. What do I do? Okay. Okay. So those are two things. The third thing is the etc. The rest of the molecule matters as well. Okay. And I guess I'm just going to say for now that the presence of other atoms affects how delta positive that hydrogen is. And I'll talk more about this in a little while. Okay, so what I'd like to do now is to go over kind of I think quite an interesting situation that we have. Wait a minute, I'm not sharing screen, am I? Am I sharing my screen? Yes. It doesn't say I am, but I am. Okay. So I just want to talk about a particular series. These are very common acids. We have the series HF to HCl, HBr, and HI. And this guy, HF, has a Ka of about 10 to the negative fourth. So it's a weak acid. But these other guys have really big Kas. These are strong acids. So we basically have a dividing line here. This is a weak acid, and these are strong acids. So the question is, why? Okay, why is HF weak, but the other three are strong? And these are from the halogens, the fluorine, chlorine, bromine, iodine in group 7 of the periodic table going down. Okay, so that's the 4 atoms that we're talking about bonded to hydrogen. So why is HF weak and the other 3 are strong? Okay, so let's talk about the bond strength first. So let's look at bond strength. So we know that longer bonds are weaker. So which of these atoms, and they're in this order on the periodic table, as you go down the periodic table, that's where they are. How will the bonds HF compare to HCl and HBr and HI? What is happening as you go down here, the size of the atoms from going from fluorine to chlorine to bromine to iodine, the size of the atom bonded to the hydrogen increases. And that makes the bonds longer. So the bonds get longer as you go down this series of atoms on the periodic table. The bonds get longer. What happens when bonds get longer? Longer bonds are weaker bonds. So bond strength decreases. Oh, well, that's nice. That makes sense, right? Okay, that would make sense that the bonds are weaker as you go down here. So that's going to make HI more willing to release its hydrogen because it's not being held by as strong a bond. Okay, so I like that one. That fits. It makes sense because HF is a weak acid, and the others are stronger. So that fits. But unfortunately, chemistry is not always, so easy to categorize and to, things don't always fit that perfectly. Because I want to show you another trend. As you go down the periodic table from F to Cl to Br to I, so as you're going down this way, the electronegativity of the atoms bonded to hydrogen decreases. In fact, you may remember fluorine is the most electronegative atom in the periodic table. Okay, so that means that the H becomes more, it becomes less delta positive as you go down this periodic table. So this would make the acids less strong, right? Going down. So this goes against the actual trend that's observed. This would imply that HI would be a weaker acid than HF, but that's not true. So this goes against the observed facts, that HF is a weak acid. Okay, So what's going on here? And like I said, chemistry, sometimes it's the things like this that make it more interesting. Okay, so what's really what the answer here is that even though fluorine is the most electronegative atom in the periodic table, it is the short bond length that makes that bond so strong that that is really the dominant factor. So I guess I would say here that we have two trends. We have the trend in the in bond strength, which depends on the size of the atoms. And then we have the trend in electronegativity, okay, which determines the polarity. And this trend here is the dominant trend. This is much more important. This is the dominant factor. And that would, because HF, because F is so small, that this bond is just very strong. And that F is not releasing that hydrogen. So, I actually almost picked to show you this one thing that where there's two trends, because, it tells you there's a lot of richness in this field. It's not all easy to understand. And, this is why we teach advanced courses and why people spend their whole lives doing research in this subject of chemistry, because there are lots of things like this. So HF is a weak acid despite the fact that it is extremely polar and that hydrogen is close to being a proton already. It's because the fluorine hydrogen bond is very short and very strong, and that is the dominant factor. So, that's just one of the more complicated things that I just wanted to tell you about, because it's pretty interesting. All right, so what else to tell you about with acid strength? Okay, so most of what I want to tell you is about the etc. So what is the role of the rest of the molecule in determining the strength of an acid? Okay, so first of all, I showed you this before, but maybe now you'll appreciate it maybe a little better. So before, when we started this unit, I showed you two molecules. Maybe you'll recognize this one. This is ethanol. And then the other one is acetic acid. Okay. Now, both of these have a hydrogen bonded to an oxygen. You have a delta plus, delta minus situation, right? You have the same type of bond. This is what I call the acidic hydrogen, which means that these other hydrogens, they will never be released. These are never going to be released. They are not acidic. They are bonded to carbons, which aren't even polar. So ethanol and acetic acid both have a hydrogen bonded to oxygen. But ethanol is not an acid. And acetic acid is an acid, obviously by its name. Okay, so the question is, why? So obviously, this part of the molecule, this is the etc., matters. Okay, this is the etc. Okay, and so what what makes acetic acid an acid is that adjacent C double bond O. Again, I'm losing this. Let's see. Oh, just a minute. Boy, this is getting kind of annoying. Okay, hopefully that's good. Something with my fans are not working well today. Not keeping this nice and cool. All right. So what was I saying? So what it is it's the presence. Oh, it's still not writing. It's the presence of that C double bond O right here that's adjacent to the OH that makes this an acid. In other words, it makes that hydrogen donatable. Okay, whereas here in this case, we do not have that C double bond O. So why does that the presence of that oxygen there matter so much? And this is the reason why. Okay, here's a C double bond O, OH, you have hydrogens here. We basically, this is already negative and positive here. But this oxygen is also very electron grabby. It also has a very large electronegativity. So it tends to pull electron density. That's how we put it. It pulls the electron density because, you know, these electrons are not very particle-like in molecules. They're really like a cloud, okay? Their location is not that certain, right, from quantum mechanics. So what we have is we have a tendency for this oxygen here, because of its electronegativity, so it has a high electronegativity, to bring electron density its way. Okay, so we have this flow of electron density. This movement of electron density in this way we call induction. So we say that the electrons kind of, the electron density moves towards the oxygen by induction. And that's something you'll use when you take organic chemistry. So the presence of this extra oxygen here, pulling electron density away from this center over here, effectively away from the hydrogen, means that the hydrogen is even more delta positive when the C double bond O is there. And that is why this group is called a carboxylic acid group. It's because this combination of having the OH with the adjacent C double bond O pulls electron density in this direction and causes the H to be more delta positive and more donatable. And so it makes acetic acid be an acid, whereas ethanol is not an acid at all. So that's a very large class. class of acids, of weak acids, called carboxylic acids. And other atoms in the rest of the molecule can also influence it. So here's an example. Here's acetic acid with all hydrogens here. And remember in lab recently, last week, you measured the Ka of this acid. Anybody remember what this acid's name was? This was from the dilutions lab. We measured the pH of a sample of chloroacetic acid. This we call HOAC. This we call HOACCl. Okay. And now you could see, okay, in both of these, we have this pull of electron density by induction this way. But here we also have an electronegative atom that will also pull electron density away from this region. Okay, and so whereas acetic acid has a Ka of about 1.8 times 10 to the negative fifth, HOACCl has a Ka that's between 1 and 2 times 10 to the negative third. So it's significantly more acidic than acetic acid. Okay, and it's just from the presence of that chlorine. So the rest of the molecule is very important. So there's one more class of acids that I'd like to talk about. It's a very large class of acids, and it's very much affected by the et cetera. So this is another sort of huge, maybe not as huge as the carboxylic acids, but another huge class of acids where the et cetera matters a lot. And these are called oxo acids. So what is an oxo acid? So I'd first like to go over, you know, we've been talking about all kinds of acids. HClO4, we never really paid much attention to the structure. H2SO4, those are oxo acids. But if I asked you to draw the Lewis structure of H2SO4, you might think that the H was bonded to the sulfur, and you would be wrong. In all oxo acids, the hydrogen is bonded to oxygen, okay? H is bonded to O. Okay, that's the first thing about oxo acids. The second thing is that that O is then bonded to some different atom. So this is number 2. The oxygen is bonded to a different atom. Okay, it's not hydrogen and it's not oxygen, other than hydrogen or not hydrogen and not oxygen, but some other atom. So that's the second aspect of oxo acids. And the third is that that other atom may be bonded to 1, 2, or 3 more oxygens. So we can have up to 3 more oxygens. You don't have to have them all. You could have 2, or you could have just 1, but you could have up to 3. Okay, so when you go and you try to write the formula of an oxo acid, you need to realize this. You need to realize that the H is bonded to the oxygen and not to that Y, whatever that Y is in the case, whatever case you're studying. Hold on a sec. All right. So let me go over a couple of examples. So for example, HClO4, that is an oxo acid. And if you look at the formula, you might think that the hydrogen is bonded to chlorine, but that's not true. The hydrogen is bonded to oxygen. Chlorine is the Y, okay? So Y equals Cl here. And then you could see that this is only HOCl. There's 4 O's. So that must mean that there's 4 more O's here, okay? Now, if I were going to write the correct Lewis structure, I would have to fill in all the lone pairs, right? I put 3 lone pairs here, 2 here, and 3 here. But generally, you know, you're not going to see those lone pairs. You have to know that they're there. Generally, when you get to be more advanced than this course, where you're almost there, right? Because organic chemistry is next, we generally leave off the lone pairs. So this is HClO4. What about H2SO4, the one I was talking about before? So this is HClO4. How about H2SO4? Okay, so the hydrogen is bonded to oxygen, which is bonded to Y, which is sulfur. So Y is sulfur here. We could see that there are 3 other O's. Oh, but I left out a hydrogen. Well, that's because this one is a symmetrical molecule and you have a hydrogen on 2 of the oxygens. Okay, so this is what we call a diprotic acid. It means it has 2 protons to give. Okay, so that is the structure of H2SO4. These are strong acids, so, you know, why? Well, I'll explain that in a minute. Here's another example of an oxo acid, HOCl. Notice that the formula is written as HClO, but that's not the structure. The structure is the H is bonded to O. Okay, so in all of these cases, the O pulls electron density away from the hydrogen. But when you have more oxygens, you get even more of that occurring because you'll be pulling electron density all the way down here and all the way over here. Okay, so you have less electron density on this hydrogen here. So it's more delta positive. And so it would be a stronger acid when you have more O's. So there are a few things that matters here. So what matters in terms of strength? Is the electronegativity of the atom Y. Okay, so one thing that matters is the electronegativity of the atom in the middle, this one here. If the more electronegative it is, the more electron density it pulls away from hydrogen. And the more acidic the acid will be. The other thing I've already mentioned is the numbers of oxygens. If there's more oxygens, the acid is stronger, because each of those oxygens is pulling electron density toward it and away from the hydrogen. Each electronegative, because it's very electronegative, oxygen pulls electron density away. Okay. So if we go back to HClO4 here, HClO4 is an extremely strong acid. Look, it's got a pretty electronegative chlorine in here. And it's got 4 O's. So this is a very strong acid. This is also a strong acid. It has 4 O's, even though it only has a sulfur, which is not all that electronegative. It's enough to make it a very strong acid. HClO has only 1 O. And even though chlorine is pretty electronegative, this is a weak acid. So it's hard to compare. It'd be easy to compare, say, HClO to HClO4, because HClO4 has 4 oxygens. This one has only 1, and everything else is the same. The Y is the same. So you would be able to clearly state, I think, clearly see that HClO is a weaker acid than HClO4. And so there are certain things that you could say, like, for example, what if you had HClO4 versus HBrO4? Which is stronger? Well, what's the only difference here?
The Y.
Yeah, the only difference is the Y. And which is more electronegative, chlorine or bromine? Remember, electronegativity increases as you go to the upper right corner of the periodic table. So this is more electronegative. You can always look on the chart. And so that makes HClO4 as a stronger acid. In fact, it's one of the 6 strong acids. HBrO4 is not listed among the 6 strong acids because it's not considered a strong acid. Actually, activity 13 has more examples of this. Here's activity 13. So here's an example that I already sort of talked about this, but this is HOCl with another O. So this is HClO2. You can see this is not a complete Lewis structure. I would have to put the lone pairs to make it complete. But like I said, you don't often see the lone pairs. Versus HClO, which would be written this way. And this is a stronger acid because it has more grabby oxygens. So you get more of this happening this way. Okay. If we looked at this set, again, this is more electronegative. So this will be a stronger acid. Okay. Here's an example where we have 2 different carboxylic acids. Here we have just 2 chlorines. And here we have acetic acid without any chlorines. Well, now we have 2 electron withdrawing chlorines, so we're pulling more electron density away from this hydrogen here, making it more polar. So this is more acidic. This would be dichloroacetic acid. So some of these are pretty interesting. And then we have on the same sheet 2 pretty interesting suspects, okay? So these are oxo acids, but they are charged. So let me draw the structures of these. So first of all, remember, the hydrogen is attached to an O. The O is attached to a Y, which is phosphorus. So first I'm going to draw this one. So H2PO4 minus. So I've got to put some more O's here, right? I've got 4 of these now. And now I have a second H. So you might ask yourself, well, why is there a negative charge? Why does this even have a negative? And you'd have to reach back to your Chem 103 to calculate the formal charges on these guys. You think you could do that? So remember, when you calculate a formal charge, it's like you're dividing a bond in half. And 1 electron goes on one side and 1 electron goes the other way. So this oxygen here has 6 electrons from lone pairs. And it has 1 electron from a bond. So it has 7 electrons. This is always the case when you have an oxygen with 3 lone pairs. That's 1 more electron than oxygen's valence electrons, which is 6. So this has a formal charge of -1. And so does this oxygen over here, because it has the same configuration. Oxygens that have 2 lone pairs, that's 4 electrons from lone pairs. And then if you divide each of these bonds in half, it has 2 more. That makes 6. So the formal charge is 0 on these, because that's the same as what it had as a single atom. Hydrogen always has a formal charge of 0. It only has 1 electron, and that's all it ever has. But notice there's a -1 charge here. Now, if it was just like this, then it would be -2. But phosphorus, what is its formal charge? If you look at the periodic table, P is directly under nitrogen, which has 5 valence electrons. But if you divide these bonds in half, you only have 4 electrons on phosphorus from bonds. You don't have any lone pairs. So the formal charge on the phosphorus is +1. So as always, if you add up the formal charges, -1 is 2 of them, -2, +1 is -1. You add up the formal charges, you get the charge on the ion. Whew, that's a lot. It's really a mouthful, but it explains why H2PO4 has a negative charge. So we have H2PO4 minus. Now I've messed the drawing up with all those formal charges. Sorry, 1 minus. Okay. And now we have another guy. We have HPO4, 2 negative. Remember that's what we're going back to the beginning of this problem. That's for the 2 we have to compare. So HPO4 2 minus, again, H bonded to O, like as in all oxo acids. Here's a P. Oh, it looks like it's the same, except it doesn't have that H. And indeed, we have a -1 here, a -1 here. We still have +1 here, and a -1 here as well. So, we have even a greater charge here of 2 negative. So we're trying to compare the ease with which a proton will be released from these, okay? And here's the thing. It's basically the same structure, but the only real difference is this one has a greater negative charge. So you have to ask yourself the question, if you're going to pull away, you're going to remove an H plus from each of these. That's what it means to be an acid, is how easy is it to remove an H plus? Well, it's pretty hard to remove an H plus from something with a negative charge, because plus and minus attracts. So let me write that down. Hard to remove a proton, which is H plus, from a negatively charged ion. Well, if it's hard to remove a proton from a negatively charged ion, it's even harder to remove a proton from something with a -2 charge, okay? So even harder to remove a proton from an ion with a -2 charge. So the bottom line here is that H2PO4 minus is a stronger acid than HPO4 2 minus, okay? Because it's got a bigger negative charge. It's got a smaller negative charge. So taking the proton away from only one negative is easier than taking a proton away from something with 2 negatives. But honestly, this whole idea of bringing up these particular ions is you have to ask yourself, well, where the heck do these compounds even come from? Why are they charged? You know, why do we have acids that are charged? Where do these ions come from? And basically they come from acids that are what we call polyprotic. So polyprotic acids have more than one proton to give. They have more than one proton, more than one H that can be released as a proton. And so if you look on our dissociation chart, acid dissociation chart, you see here's carbonic acid. Carbonic acid has 2 protons that it can give up. It gives up one, it becomes HCO3 minus. It could give up another one. Notice that there are 2 different Kas. Okay, this is the Ka for releasing the first proton. This is the Ka for releasing the second proton. And just to talk about phosphoric acid, here are the 3 different chemicals that are listed here. And these 2, the ones with the red arrows, are the ones I've been talking about. And you see that phosphoric acid, this is a pretty strong acid for a weak acid. It's about the strongest it gets for a weak acid. You could remove a proton, you'd have H2PO4 minus. You could remove another proton, but look, the Ka is smaller. You could remove a third proton, but the Ka is smaller still. So what I'd like to do is show you what these Kas are referring to for phosphoric acid. So here's phosphoric acid, and then the 2 other chemicals that can be that come after you give up a proton. So H2PO4 minus and HPO4 2 minus. So here is the first acid dissociation. This guy gives up a proton to water, and you lose a proton here. So you are H2PO4 minus because you've given up a positive. And the Ka for this, I call it Ka1. It's the first dissociation. And it's a bigger number, 6.9 times 10 to the -3. So that's pretty strong, like I said, for a weak acid. So that's releasing the first proton. But you can also release a second proton. So you would start with H2PO4 minus. Donate a proton. You would get, now you're removing a hydrogen. So instead of H2, you have H. still have the PO4, and now you have a -2 because you've taken away another proton. But look what happens to the Ka. This is the Ka for H2PO4 minus. This we would call Ka2 for H3PO4, but maybe it's better to just think about it as a Ka for H2PO4 minus. And that's 6.8 times 10 to the -8th. Look at that. It's 5 orders of magnitude smaller. So, and actually, this is what I was just talking about. Here, you're taking a proton away from a neutral compound. Here, you're taking a proton away from a negatively charged compound. It's much harder to do. And that's why this number here is much smaller than this one. So I would say this is smaller because the H plus is being removed from a negative ion, and plus and minus attract. So it takes a lot of energy to do that because it's not, it's not a downhill process. It's unlikely. Well, let's try releasing the third proton. So you would start with HPO4 2 minus and water. Now you end up with just phosphate, PO4 3 minus. And the Ka, which is the Ka for HPO4 2 minus, is even smaller still. Look at this. This is like about as small a Ka as you can get. Okay. And the reason is here, you're taking a proton away from something that has a -2 charge. So this has a -2 charge. It's even harder to remove this proton. So that's what happens. That's the kind of the complexity of the chemistry that you have when you have a polyprotic acid. And if you notice on the chart, of course, I showed you that these are all in the weak acid dissociation chart. But let's not forget that the same chemistry that we have for all acids also goes for these. When you remove a proton, you now have the conjugate base of that acid. So I guess I would say that H3PO4, H2PO4 minus, and HPO4 2 minus are all listed in the weak acid chart. But don't forget that H2PO4 minus is the conjugate base of H3PO4. And HPO4 2 minus is the conjugate base of H2PO4 minus. And you know that, sometimes things behave as acids or bases according to the company they keep. But how would they behave with water? So I guess you have to really ask yourself the question, H2PO4 is a weak acid on the weak acid chart, but it's also the conjugate base of H3PO4. So is it basic or is it acidic? Okay. Now H3PO4 is a pretty strong acid, which means that H2PO4 minus would be a pretty weak base, because the stronger the acid, the weaker the conjugate base. But HPO4 2 minus is the conjugate base of a much weaker acid. So is it a base or is it an acid? So I just kind of want to finish by saying, how can you tell if H2PO4 minus or HPO4 minus is an acid or a base in water. Okay, so what you have to do is you have to figure out, let's take H2PO4 minus. If it acts as an acid, then we know what it does. It donates a proton, as I've showed you already. And we know the Ka for this because it's on the chart. It's the second one down, right? It's this one. This is the Ka, 6.2 times 10 to the negative 8th. The question is, what if it acts as a base? If it acts as a base, it'll accept a proton from water and form H3PO4 and hydroxide. So the question is, what is the Kb equal to for this? Because what you have to do is you have to compare the Ka for if it acts as an acid to the Kb for if it acts as a base. And the one that's larger wins, okay? Whichever is larger, that's what it's going to be. Yeah, I can't get a pen back here. All right, so we know what Ka is, but Kb, well, now we could go back and we can use the fact that Kb for any conjugate base is Kw over Ka for the corresponding acid. So Kb for H2PO4 minus is Kw over Ka for H3PO4, which is 1 times 10 to the negative 14th over, and remember the Ka for H3PO4 is pretty large. If we look it up on the chart, it's 6.9 times 10 to the negative 3. This is going to be a pretty weak conjugate base. Okay, so this turns out to be 1.4 times 10 to the negative 12. So that's Kb for H2PO4 minus. So here's the Kb, and here's the Ka. And if you compare these two, this one is larger. So what does that tell you? It tells you that H2PO4 minus is basic. Wait, sorry, acidic. Because the Ka is larger. Okay, so to figure out whether this is true for the other ion, Na2HPO4. All right, so suppose now we're looking at the HPO4 2 minus ion. Where would that ion come from? Well, it could come from sodium hydrogen phosphate. That's what this is called. You don't need to know that name. You see there's two sodiums. Sorry, it doesn't charge anymore. There's two sodiums because you have two negatives here, so to balance the charge. So what ions are present, of course, is the sodium and the HPO4 2 minus ion. Okay, we know sodium is neutral. So we're trying to figure out if this salt here, sodium hydrogen phosphate, is acidic or basic or neutral. So it all depends on this ion here. So this is a special problem. I'm not going to do it now. And I would say you should do it if you're interested in it, you know. It's not a hugely important part of this course, but it's an interesting problem. And so what this problem asks you to do is to write the chemical reaction if HPO4 acted as an acid. In other words, what happens when it reacts with water and donates a proton, okay? That would be it acting as an acid. And here, under here, to do the same thing, but for it acting as a base. So it would have to, H+ would have to go the other way. And then it asks you to compare the Ka for HPO4 which is given in the chart right here, to the Kb. And then figure out which is greater, and that by that determine whether it's acidic, basic, or neutral. This is going to be due Friday, the 23rd, because I know you're still working on that test. So I just wanted to say that. So I'm actually done with acids. Yes, I know it's a lot to absorb, but if you have any questions, please, you know, ask them. Ask them right now or later, whenever you want. I'm pretty much done with what I had to say today. So you'll see that there's two special problems, that activity 11 and 12. I said it was 12 and 13 last time, but I was wrong. So you'll see there, there's a space to submit them. I have to put one in for this one. This will be called SPHPO42- or something like that. So look on Blackboard for that. This is not up there yet, but I'll put it up. I hope the exams are coming along. How are you doing with those? I got a thumbs up. All right. One thumbs up. Good, good. All right, good, good. Oh, good. Submitted today. All right, good. Yeah, I just opened it up yesterday because Chelsea reminded me. I didn't even have it up there, but it's up there now. All right, and I said it was due Friday. You know, if you need more time, just email me, okay? All right, that's all I have to say today. So yeah, I'll see you Monday. Oh, wait, Monday's a holiday. I won't see you for a week. A week, yeah. Yeah, I'll see you a week from. I'll see you on Wednesday next week. Yeah, yeah, see you Wednesday, right? Okay.